Okay, today we're going to talk about functions of several variables, or what are also called multivariable functions or multivariate functions. Okay, let's look at this one here. F of xy equals the square root of 1 minus x squared over 9 minus y squared over 4. Okay, this is what's called a function of two variables. You can see that, right? There's an x variable and a y variable. Okay, so let's think about what would the domain look like. Well, first of all, where would the domain be? And what sort of things are you putting into here? Are you putting numbers into this function? Well, you might say we're putting in two numbers, a number for x and a number for y, and that would be correct, but I would like to point out something at a little bit of a deeper level. Because you're plugging in a pair of numbers, x and y, then what is it that you're really plugging in? You're really plugging in points. You see what I'm saying? The input are points, and the outputs are going to be numbers. Correct? You calculate, what I'm saying is you calculate this number here. You plug in an x and a y and you calculate that number, and that's your output. Okay, so the inputs are points and the outputs are numbers. Where do the points live that you put into the function? You know, where are they coming from? So think about it. They're points x and y, right? So where are those points going to come from? They're going to come from the xy plane. That's where the points are coming from that you're plugging in. So let's write where I put it that the inputs are points. Let's be more specific and say that they are points in the xy plane. Now, where are the output numbers going to be? Well, where's the only place left for them to be coming from? Or where do they live? There's only one place left, right? And that's the z. Just a second here. So let me write the z. Now, how many letters are there? Just one, right? Z. So do I say in the z plane? No, that doesn't make any sense. There's no such thing. Planes have to have two dimensions. If you only have one dimension, then you're a line. So it would be the z what? The z axis. And so I should say numbers not in, but numbers on the z axis. Okay? I'm not saying that when we graph this, all of the... Whoops, I went too far. I'm not saying that when we graph this, all of the points are on the z-axis. That's not what I'm saying. What I'm saying is this. Okay, what if we plug in the number... Sorry, not the number, the point, square root of 7, comma 2/3. What would we get coming out? Let's do this, write this in a different color. Let's write this in dark purple. Okay. So what would that equal? let's see. Let's do some scratch work here. So we would get the square root. Here, let's do this. Let's write it carefully. I'm going to write f of square root 7 comma 2/3. That would be the square root of 1 minus square root 7 squared over 9 minus 2/3 squared over 4, which would be the square root of 1 minus 7/9 minus 1/9. So that would be the square root of 1/9, which is 1/3. So our output then would be 1/3. Okay? Now, what would be the corresponding point on the graph? Okay, let's write that down. The corresponding point on the graph would be the point square root 7 comma 2/3, that's your x and your y, comma your z, 1/3. Now this should actually make sense when you think about it. Think back to calculus 1. Let's just compare this situation to the situations that we dealt with in Calc 1 and Calc 2 when you were graphing. Okay, let's suppose we had f of x equals 5x plus 1, let's say. And let me go ahead and put a xy axis here. Okay, so what would we have done? In Calc 1, we would have done something like this. Input two gives us an output of 11, and the corresponding point on the graph I misspelled that. Would be what? 2 comma 11. Very similar, you see. Now, how would you actually go about graphing that? Well, wouldn't you have the point here, 2, 11, right? But here's the thing that a lot of people miss. If I asked you, where does the input live? You should say this. Here's the input right here. Oops, wrong color, sorry. You should say, here's the input. Right there is 2. And most people would answer that correctly. But here's the question that a lot of people answer incorrectly. Let me get dark purple color here, and let me ask you, where's the output? Most people will say, well, the output's right there. And that's wrong. The output is not the point 211. The output is 11. Where's the output live? The output lives right here. Whoa, I didn't mean to erase everything. The output lives right there. You see, you have input, whoops, input on the y-axis, output on the z-axis. You go to where those things meet, and it gives you the corresponding point on the graph. Okay? So now, in this multivariate setting, it's a very, very similar idea. You have input. In this example, we could have plugged in lots of different points, but I plugged in the point √7, 2/3. So where is that? That's right about here. That's an input right there. It's √7, 2/3. Okay. They meet right there. So again, I want to point out, some people would say, I'm inputting two numbers, the numbers √7 and 2/3. Some people would say, I'm inputting one point, the point √7 2/3. Both of those are acceptable ways of saying it. Okay, now, what do we get as an output? We get the number 1/3. Okay, so where is that? That is going to be, let's just say right here. What's the corresponding point on the graph? Would be input, output. So 7, 2/3, 1/3. And that would be right there. So we have input, output, corresponding point on the graph. By the way, let's just see that that is where you go straight up from the input point and straight over from the output number, and you get the corresponding point on the graph. Okay? That's how you graph these points. So let's go back to this stuff right there, okay? If the inputs are points on the xy plane, then let me ask you a question. Where then would the domain be? I'm not asking you to find the domain, I'm just saying where would it be? Darn. Isn't it true that the domain would be an area in the xy plane? If the inputs are points in the xy plane, then the domain consists of points in the xy plane. So in other words, the domain is going to be some area in the xy plane here. Let's find the domain for this particular function. So look at our function. F of xy equals the square root of 1 minus x squared over 9 minus y squared over 4. What is the restriction on square roots? The number inside can't be negative, right? The number inside has to be equal to or greater than 0. So for this function, I would write 1 minus x squared over 9 minus y squared over 4 has to be equal to or greater than 0, which means negative x squared over 9 minus y squared over 4 has to be equal to or greater than negative 1. Which means x squared over 9 plus y squared over 4 has to be equal to or less than 1. That's our domain. What is that shape? that is the region inside the ellipse x squared over 9 plus y squared over 4 equals 1. So our domain would be the area on the xy plane that is inside that ellipse. Okay, actually I should write this equal to, or less. There we go. That's what the domain would be. I can show you a picture straight from the book, so it's a little bit nicer. Okay, so there you go, is a better picture of the domain, okay, of our function. Now, what do you think the graph of that whole function looks like? The graph, remember, is going to consist of points that are hovering above the domain, not on the domain, hovering up above it. Okay, what do you think it's going to look like? Well, it's really hard to tell. Let me show you. There, you see the picture? It's like a dome over the ellipse, which is the domain. Okay, this ellipse right here, that's the same as right here. Okay, and that is also in this picture down there on the bottom. You see that ellipse down there? That's the domain. The graph of the function is this dome up above it. Okay, that's how you graph multivariable functions. How do you think they found that dome? Like, how would you find that dome if you had to do it? Well, you would just be plotting a whole bunch of points. It's not as simple as it was for graphing things in Calculus 1 and Calc 2. Graphing things here like this, multivariable functions, requires you to plot many more points in order for you to see the shape. They're also difficult to draw accurately because they exist in 3 dimensions and you're trying to draw it on a flat 2-dimensional surface. So therefore, usually when people have to graph these things, they do them with a computer graphing software, which is how that dome was made. Somebody did not do that by hand. They did it on a computer. Okay. Now, the last thing to talk about is, what do you think these circles are that are on there? Why do you think those are there? Okay, let's talk about those. Those are called level curves. Okay, let's get some space here. Give me a minute. I'm going to free up some space. Okay, so those circles that are drawn there, those are called level curves. They are exactly analogous to the lines that you see on a topographical map. You see all those lines in that picture? Let's make it a little bigger. Okay, for instance, let's look at this. You see that number 5600 right there? And then you see that line that goes through there. Not really a line, but this path. You see that? So that's a line that is showing you all of the connected points on the map that are at an altitude of 5600 feet. If you walked along that path, you would not be going up or down. You would remain at a constant altitude of 5600 feet. here is the level curve for 5,400 feet. That path traces out a path with a constant altitude of 5,400 feet. Okay, here's one for 6,200 feet. There's a whole bunch of them drawn, right? But some of them are darker than others, and some of the darker ones are even labeled with numbers. So that's what level curves are. Go back over here to this picture. You see those circles? Those are level curves. The one that I've pointed to, here, let's get rid of this now. We don't need that anymore. The one that I've pointed to, that's the level curve for the number 0.6. Let me write this here, level curve, and then in parentheses I'm going to write C equals 0.6. Okay, so that is the points on the graph that are all at a height of z equals 0.6. Okay, I've been calling them circles, but they're actually not. They are ellipses. Let's find that specific level curve right there. Okay, so what would I do? I would write f of xy equals 0.6. So that means the square root of 1 minus x squared over 9 minus y squared over 4 equals 0.6, which means 1 minus x squared over 9 minus y squared over 4 equals 0.36. Which means negative x squared over 9 minus y squared over 4 equals negative 0.64, which means x squared over 9 minus y squared over 4 equals positive, well, that should be a plus there, sorry, positive 0.64, which, by the way, is 8 squared. No, not 8, rather it's 0.8 squared. I'm going to write it that way. So I'm going to write 8/10 squared, okay? Okay, so finally, that would give us x squared over, let's see, would be here 10/24 squared, okay, plus y squared over 10/16 squared equals 1. That's the level curve for the height of 0.6. And that's an equation of an ellipse, right? Let's replace our picture of our domain with one showing the level curves. Whoops. Okay, there's our domain again, but this time with the level curves being shown. Okay, and this one right here that I've drawn an arrow to, Okay, that one is right here in the picture. You can see right there. It's this one right here. And here's the equation of that ellipse right there. Okay. Now, something interesting, okay? The level curves are part of the domain. So, okay, you see where I drew an arrow here and I said level curve? Well, technically that ellipse that's hovering up there is technically not the level curve. The level curve is technically down here in the domain, as some people say it, okay, and some people say it's up here on the graph. You just have to be, you have to pay attention to the context. That's all, okay. Don't worry about that. Let's not worry about that so much. But technically, this is the equation of the level curve, and that is the equation of an ellipse in the xy plane. Okay. How many level curves are they showing over here in this picture? 1, 2, 3, 4, 5. I see 6. Do you see all 6? Probably not. I bet you only see 5, huh? Let's count them. So there's 2 right there, really close together. And there's a third one, and then a fourth one, and a fifth one. Where's the sixth one? It's, oh, what happened? It's right there. It's just 1 point. That's a level curve for c equals 1. Let's figure out why that's just a single point. Let's go back over here and let's do our math here. I'm going to write f of xy equals 1. So the square root of 1 minus x squared over 9 minus y squared over 4 would equal 1. So 1 minus x squared over 9 minus y squared over 4 would equal 1. Which means negative x squared over 9 minus y squared over 4 would equal 0. And there's only one solution for that equation. Look what happens. We get negative x squared minus y squared equals 0. So x squared plus y squared equals 0. And the only solution is the point 0, 0. Okay? That corresponds to that location on the graph. Let's go through all 6 level curves again. Oops, I erased the shading on the inside. I didn't quite mean to do that. Let's see if I can try to avoid that. Okay, so let's go through all 6 level curves. In the domain that they've shown, and let's find the corresponding locations on the graph. So this level curve that we see on the outside there, that is the level curve for c equals 0. Those are all of the points whose output is 0, and that corresponds to that ellipse there on the bottom. This one here. Okay. Now, that next level curve that's just on the inside of that one, I don't honestly know what height that corresponds to. I can guess. 1 second. I bet it's probably c equals 0.2, I bet. And that corresponds to this ellipse on the graph. Okay. The next one, third one in there, They haven't said, but I bet that's probably c equals 0.4, and that corresponds to that ellipse on the graph, all at a height, all at a height of 0.4. Okay, and then we've seen the other one already before. This one right there, that is c equals 0.6. In the graph, that corresponds to that ring. And then the next one going in, I'm pretty sure that's probably c equals 0.8, and that corresponds to this ring. And then the middle one that we looked at a minute ago, that's just 1 point. That's c equals 1. Even though it's only 1 point, we still call it a level curve. We don't call it a level point. Okay, and that corresponds to this point right at the top of the dome. Okay, how many level curves are drawn? We already said that a minute ago. There was 6. Does that mean there's only 6 level curves? No. It means they're only showing 6 of them. How many level curves are there? Well, there's infinitely many. You could draw billions and billions of level curves. Obviously, you don't want to, because then the whole graph would just be covered in level curves. And if you have too many to look at, you end up being able to see none of them, because the whole graph would just be shaded in dark blue instead of being able to see dark blue rings. Just the whole thing would look like one big dark blue blob. So you purposefully do not want to draw too many level curves, because then it gets so crowded that you can't even see them anymore. Okay, I think that's about all for this lecture. We haven't done any calculus here. It's just getting used to graphing things. And in the next lecture, we'll start looking at some limits.